do y'all have anything you want to talk about or ask about? I suspect the answer is no, but it seems like a good thing to ask. All right, that seems like what I expected. That's good. Onward with continuity. I spent some time on that Cantor problem, and it's actually kind of brutal. And also, there is this problem that I gave you all where, oh, this is what you had asked about, Lynn, I think. Is that compact? And I spent a lot of time working on this one yesterday. I don't know, did you actually get something with tiny shrinking intervals? Because I couldn't get that exactly.
I couldn't like do the math, but I just worded it that way.
Yeah, I couldn't get a cover that failed to have an open cover on it, but there is kind of a trick. I guess the only person who can act on this is maybe Miss Olivia there, but since it's only the rationals in here, only the rational points, one could pick an irrational in here, and I always like this guy just because he's nicely situated at 0.707, so it doesn't actually look like that, it looks more like that. But you could think about the fact that you don't have that element in the set, but you could get close to it. I don't know how much to say here. The sets that I ended up using are infinitely big sets, and they're kind of shrinking toward that point that's not in the set. So I can get arbitrarily close to that with infinitely many sets, but a finite number is going to fall short. Any finite number is still going to have a little gap in there because of the density of the rationals in there. There'll always be a rational you didn't hit when you have a finite cover. So that's what I came up with. I look forward to seeing what y'all came up with. And we're just here to learn, of course. All right, excuse me for taking a moment here. Okay, so last time, we're supposed to have some kind of freaking quiz today too, right? Yeah. When do you want to do that? Do you want to do it now and get it done with, or like save it for the end? What do y'all want to do?
The end? Is that crazy to say?
No, it's not a bad thing to say. Okay, there's two people nodding at the end. Then we'll do it at the end. That's great. Okay, cool. So, let me just see what you remember. Here's a quick practice for the quiz. Say definition. And we're going to call this definition 1 of continuity. A function f from D into the reals, and that's its natural domain, or it's just the domain we're setting, is continuous at x naught in D if what? Just check yourself. I won't check right now. What is that definition of continuity we know? That is some funky tea I'm drinking. You got some, Christian? What were you thinking?
I was thinking that if for any sequence at like x of n contained in D, as x of n approaches x sub naught, it follows that f of x of n approaches
So yeah, that's perfectly right. So it's what's kind of weird is that we define continuity at a point. You think of continuity as this property of moving through infinitely many points, but somehow mathematicians have figured out how to quantify it or qualify it at a point. Very strange. I just want to add this extra definition. We say that f is continuous on D, continuous on a set, if it's continuous at every point inside there. So I just want to get that out because I know I'll say it. If f is continuous at every x not in D. But just remember, continuity is a point property. Strangely, a point property. So I want to talk about a different definition today. So we're going to have definition 2 here, and you really need to be able to understand both these. And then I'm going to give us a third definition, which is a weird ass definition that I feel like it's important that you see, because it helps us understand the power of topology and the idea of open sets and closed sets. So definition 2 is, it's again going to be at a point. So I've got a function, f, which maps from some domain into the reals, is continuous. I might even write this one 2 ways. At x not in D, if for every epsilon greater, there we go, we got good old epsilon in there, there exists a delta greater than 0. Call response such that if x minus x naught is less than delta, that implies that f of x minus f of x naught is less than epsilon. This is you might have remembered this. I don't know if you saw this in calc. I'd be shocked if your calc teacher talked about this. I know I wouldn't, because like people in calc just aren't ready. They just, most of them, some of you would love that if we did that in calc, but other people would lose their minds completely. So let's draw a picture, and actually let's rewrite this one special way. Notice that this thing here is a ball. It's for every, so the collection of x that satisfy this equation is a ball centered at x naught of radius delta. Does that make sense? Do you see how that is? That this is the same as this? And this over here is a ball centered at f of x naught of radius epsilon. So how could we rephrase this? We could say, i.e., for all epsilon greater than 0, there exists a delta greater than 0, such that if x is an element of this ball, then f of x is an element of this ball. And I'm going to say that one more time, i.e., so everything that's in here gets mapped into this ball here. So i.e., f of this delta ball. And this just means take f of every point that's in here, look at the image of this ball on the output side, that is contained in this ball. And I'm going to draw some pictures to help, because I know right now it's probably seeming like kind of a little blah, a little weird. But once you see a picture, it's going to make a lot of sense. But this way of thinking in terms of these balls is really helpful, really powerful mental image of continuity. All right, so let's do make yourself a little picture. This is going to be f of x on this axis, that's x on that axis there. And we know that at a minimum for continuity, we need to have the function defined at that point. So I've definitely got a dot at that point, or above x naught. So what does it mean to say I'm continuous? Is that for every epsilon greater than 0, there exists this delta. So now the epsilon happens here. So for every epsilon tube you can make around the target, f of x naught. So right now, just take a little note here that this is a ball at f of x naught of radius epsilon. That's what that epsilon tube is. Well, that's not what the tube is, but that's what its image here is, and we can extend it outward like that. That no matter how tiny I make this tube, there is a range of responses down here. In other words, a delta ball around this input, so that all these inputs land inside that tube. So I'm going to draw little arrows here. So I'm going to actually kind of put those guys out there and arrows in that direction. Because this is something you're saying to me, oh, hey, can you get the entire function output to be in the tube of this width? And I say, yes, I definitely can. I can just pick delta small enough to make that true. Now, let's talk about this just a little bit more. I'm going to do the same picture again. So this is x naught. This is f of x naught plus epsilon minus epsilon. And again, this is the call right here. This is the thing that's given to me. And if f is continuous, I can always find a little ball around here so that the function above that ball sticks in that strip. Now, let's take a look at a bad delta. So this would be a bad delta right here. If I made this go all the way out to here and all the way out to here. Notice then that the function values, that's a super shitty asymmetric ball. But notice that these x values here don't all land inside that epsilon tube. So this delta is too big. Does that need a little clarification? Yeah, a little clarification, yeah. Cool. So if I say, Christian, that you give me this tube up here, and my job is to find a range of x values around x naught, that where the function right above those lives totally in there.
I see what you.
Do you see what I'm saying? So these spill out.
Yeah.
Okay, cool. Spill out. I just had to start like saying it's a different, just slightly differently, and you got it.
That
Okay,
makes sense.
cool. Notice also that there's not a unique delta. Once you have a delta that works, all smaller deltas also work. You can just make tinier tubes here, and of course all that stuff will go inside there as well. So how do we actually implement this? Let's take a look at a simple proof using this method. The proof. Show, here's the problem, then we'll get the proof. Show that f of x equals 7x plus 3 is continuous on R using definition 2. So this is the epsilon delta proof. I'm going to do a little scratch. scratch here. And the scratch is, I'm gonna narrate it a little bit. We need f of x minus f of x naught to be less than some given epsilon, given epsilon is greater than 0. I need that here. And so we compute the range of inputs about x naught that make this true. i.e., find the corresponding delta. So now this delta is going to depend upon, so I'm going to put equals. It depends upon the spot that I'm at, and it depends upon the epsilon. So that's what this notation means, is that this delta will change if I change the epsilon, and it will change if I change where I'm looking for continuity at. And you'll see that in just a second here, I think. So what we do is we kind of start with this assumption here, or not assumption, just this expression, and we write it out. And of course here, x naught is a real number. It comes from the domain, but our domain is everything. So you write this out, and then you literally do the computation. So that's 7x plus 3 minus 7x naught plus 3. Stop for a second. And can you just take a minute and simplify that expression? What do you notice about that expression? There's a certain direction we want to go, but I want to hold off on saying it. Do you notice any low-hanging fruit? Cormac, what are you seeing?
Knock off the 3s.
Yeah, I got 3 minus 3, so those definitely cancel out. Let's just do a little bit at a time. Absolutely. Anything else?
Factor up to 7.
Pull out that 7. So this is 7 x minus x naught. Yeah, thank you. Is everybody seeing how that worked? Make sure you see how the math worked on that. Now notice that this thing here is the thing we get to control. That's this piece right here. And I can make this as small as I want. And by making this as small as I want, I know I'll end up multiplying it by 7. And as long as that is less than epsilon, then I'm good to go. So continue the scratch right up here. So let's summarize that really quickly, i.e. f of x minus f of x naught equals 7x minus x naught. And I want that to be less than epsilon. So given that epsilon, my goal is to convince the reader of my proof that if I make this a certain size, I will be less than epsilon. So now solve for x minus x naught to see what we get. And what we do get is epsilon over 7. This is my delta right here. So this will be our delta. Let me just kind of do a quick IE here. If x minus x naught is less than delta equals epsilon over 7. So see, now I've got a formula. For any size epsilon you give me, I can compute the delta just using this formula. So if this happens, i.e. x minus x naught is less than epsilon over 7, then that means that, and this is kind of the proof we're about to write out over there, 7 times x minus x naught is less than epsilon. Let's multiply both sides by 7. And that implies that 7x, and I'm going to just go back to the stuff I canceled out. 7x plus 3 minus 7x not plus 3 is less than epsilon. And I'm inserting these guys because I'm doing the math magic that I did backwards. We've done this. This is like part of doing proofs, right? The magic on the side looks like you're a genius when you pull it together forward. So this is essentially going to be our proof. Let epsilon be greater than 0. And set delta equal to epsilon over 7. This is what the proof is about. I need to have a formula for the delta given any epsilon that's positive. Then, if x minus x naught is less than delta, I'm basically about to copy all that stuff I just wrote over there. We have, I'm going to add nice words to it. We have 7. We have x minus x naught less than epsilon over 7 implies 7. X minus x naught is less than epsilon implies, and now I'm just going to go for the kill here, 7x plus 3 minus 7x naught plus 3 is less than epsilon. And this, and then you might as well go all the way, this is f of x minus f of x naught is less than epsilon. And let's do a picture here as well. This one's got a great picture. It's very accessible. It's something we can totally understand. Because it's a nice line. So I've got this line that goes through 3, and it's super steep. So this is f of x equals 7x plus 3. Super steep line. Let me stop and let you get caught up. And I think this picture will actually be very helpful in understanding what's going on, if it hasn't been that clear yet. So if this is x naught, I'm going to come up here, and this is going to be f of x naught, which is 7x naught plus 3. You tell me what your epsilon target is up here. So you gave me that epsilon. And now by my formula, I know that delta just has to be a 7th of that. So think about how you might compute delta visually. You might go, oh, well wait, as long as I don't go past this mark here, and I don't go past this mark, oh, these lines are terrible, and I don't go past this mark in this direction, all the inputs are going to land inside that tube that I'm interested in. So this turns out to just be epsilon plus epsilon over 7. And this turns out to be minus epsilon over 7 units in this direction. Just remember, your line has slope 7. So it's going to multiply the scale. It's going to scale all the inputs by 7 and then shift them up. So that tells me that this is my delta. Delta is epsilon over 7. Anything bigger than that is going to fail. All right, let's kind of look at something. Actually, I'm going to give you one to do real quick here. Mostly because I have to pee. So let's just try one and see how it goes. I put a little bit of a trick on it. If f of x equals negative 2x plus 1, show f is continuous at any x naught in the reals. Take a minute. I'll be right back. Anybody got a delta for me yet?
Does our delta have to be greater than 0?
It does. That's why I put that -2 in there to be a crafty bastard. Yeah, delta will be a positive number as well. It's a good question, Courtney. What'd you get?
Epsilon over 2.
Let me kind of do the scratch. Key thing is you always want to get this x minus x naught in there. There's a little bit of a trick just with that minus sign. And you can only pull out the absolute value of -2, which is just 2. And generally by the time you've done the scratch work, you've got your proof in order. You just unfurl it backwards on paper with some words. Realize that these are these implications. This thing goes up and down. If one is true down, same flow is true upwards. So it's like an if and only if flow. Let me stop. Let me make sure everybody's got a chance to just finish up their proofs. And I want to do something a little bit funkier because, of course, we want to get funky. One thing to notice is that this example and the last example, the delta didn't really depend on the x naught, but it could. It's going to in the next example. Here it's just depends on the epsilon, but it's something you should expect that delta will depend upon the epsilon, and especially when you got this, when f is nonlinear. Or f is something we will get to. F is uniformly continuous. And we'll talk about what that means. But it basically means your delta doesn't depend on where you're at. So is there, should I explain at all about how to get that epsilon over 2 for our delta? Is everybody feeling okay about that? Camila, you good? Cease, you good on that? Liv? Yeah. Okay, cool. So then I just unfurl. This is all backwards. So I said this. Thus, use some thus words, hence, whence, thus. Thus, if x minus x naught is less than delta, we have x minus x naught is less than epsilon over 2. And then this is something, you wouldn't see unless you were the one who made it. So that's 2. Take some time. And then this next one, this is going to be the mysterious one here. Let's see, so I had -2x plus 1 minus -2x naught plus 1 is less than epsilon. And bringing it home, that's just f of x minus f of x naught less than epsilon. So this is a lot more work than that limit definition that we had, but it's an important way to understand how to think, because at some point we're gonna need to think like this. So I don't know if any of the homework problems, I hope I gave you some where you had to do this. Anybody know yet?
I think so.
Cool, okay, that sounds good. I'll take that. That sounds really good. All right, let's do another example unless there's some questions on that one. Let's do a nonlinear thing. So show f of x equals x squared is continuous on every place, on the entire real line. We kind of know that. We know it's a parabola. We can picture it. There ain't no holes. There ain't no jumps. It's a pretty old parabola. Let's put it up here just to appreciate how beautiful it is. I'll try to make a decent one. Good old parabola. Yeah. And you can kind of see, just like really quick, just take a look at how epsilon and delta would change. So if I'm in here, and that's my x naught, I come up here, and then you give me that little epsilon, that's plus epsilon minus epsilon. Look at what the delta would be there, as opposed to out here. So notice the relative change in the width of this versus the width of this. Whereas if I'm out here, there's f of x naught right there. And I move up that same epsilon. So there's the plus epsilon, and down the same amount on epsilon. Look at how much skinnier over here it's going to be, because the slope there is a lot steeper. So it's not a great drawing, but you can see the delta here is a little thicker than the delta ball over here. And then the further out you go, the worse it gets. So we can see that delta is going to depend on where I'm at, not just the epsilon that I set. So let's do our scratch before we do our proof. And this has got a trick in it that I want to show you that I think you will need. So I take f of x minus f of x naught, set that less than epsilon. Take a pen, not a good pen. That's killer good pen. All right, so what does that mean? That means x squared minus x naught squared less than epsilon. So I'm gonna ask for your help here, because what I'm shooting for is somehow I need to take this expression and find in it an x minus x naught. Just like we did over here. We needed to get that x minus x naught thing in there. Any suggestions on how we could at least move closer to seeing that? How could you pull an x minus x naught out of that expression?
Or I guess it's x naught.
I'm sorry, what are you saying?
It wouldn't work.
Okay, all right. I don't get it. Anybody remember factoring? Good, cool. What kind of factoring does this dude do?
X minus x naught times x plus x naught.
Difference of two squares, exactly. So this thing I'm gonna factor is x plus x naught, I'm gonna put that in front, times x minus x naught, and I need that less than epsilon. So this is cool, this is what I want. This is not good here. I wish this was like a 7 or a 2 or -2 or something. I wish this was a constant. So it's a problem that this is not constant. We're gonna make it constant by making an extra assumption. So we're gonna add in an assumption of our own to make this thing at least something we can get a bound for. It's okay to set an upper limit on your delta. And that's where the trick here is. Because as long as we say that delta can shrink as much as we want, it's no problem. And so the trick here, let me just write this out, set an upper limit on the delta. You'll see how this works. You've probably never seen this before. So just bear with me while we work through it, and I think you'll see how it paid off for us. So i.e., assume that delta is less than or equal to 1. That's a pretty big delta because most of the time we're worried about super tiny deltas. So, i.e., this would mean that x minus x naught, if it's less than delta, is going to be less than or equal to 1. So let's just pull away the delta. Now I've got that there. And I'm going to write out what that means as a double inequality. Okay? Check it out. And look at what I've got here. I need to somehow get an upper bound on this. So what kind of manipulation could I do to that double inequality? Let me write up here kind of the motivation. We want an upper bound on absolute value of x plus x naught. And once I get that, if I know this is never more than 20, then I can use that to treat it like it's a constant. So any suggestions on how we could move to just getting this expression in the middle here? What would you do? And remember, x naught is a constant.
Well, I have a question.
Yes, sir.
How did you go, so you assume delta is less than or equal to 1.
Yes.
Why does that mean x minus x naught is less than delta?
Because at some point, yeah, that's a good question. So at some point we're trying to find this delta here. That, how about we say, actually this, I think I missed a word here, that if this holds true.
Okay.
That sound better? Yeah, that's a really good point. That if this is true, then this is true, then this is true. Yeah, good point, Howard. How do I move that middle piece to x plus x naught? What algebra do I need to do? Nothing heavy, don't get too crazy.
Just divide by a negative.
If I do that, so if I
like
do,
negative x plus.
then I get a negative, and I still want a positive, yeah.
Add 2x naught.
Add 2x naught. Just add 2x naught across, that's a constant. So add 2x naught to each part. And then we're going to get 2x naught minus 1 less than or equal to x plus x naught less than or equal to 2x naught plus 1. And now we can actually say something. So x plus x naught, so if x minus x naught is less than or equal to 1, or even strictly less than 1, but we'll just leave it like this, then this is less than or equal to the biggest of these magnitudes, the biggest these things could be. So let's try to think about what is the biggest magnitude this or this could pump out. And if you think about it a little bit, you'd realize that the biggest magnitude would be obtained when I took the absolute value of the x naught and then added on a 1. So that's a nice positive number. And both this and this cannot be more than that in magnitude. So let me stop and see if you believe me. seems kind of reasonable. If you took a few minutes, you could probably convince yourself of it thoroughly. And this should say plus, sorry. This should say plus here. Now we're gonna put some things together. We're kind of actually gonna continue on with this little doohickey here, so I'm gonna call that star. So I'm just copying star over here. It says this, the absolute value of x plus x naught times x minus x naught is less than epsilon. Since absolute value of x plus x naught is less than or equal to 2x naught plus 1, absolute value, when x minus x naught is less than 1, less than or equal to 1, that means that this side here, we know that x plus x naught times x minus x naught is less than or equal to this thing for this times absolute value of x minus x naught. So I got a bound on this chunk, and I'm saying this because of it, because of the work we did a little earlier. So we got an upper bound on this, and this is only true when we are not more than 1 unit away from where we're at. But this is going to help us get our delta. So we want this to be less than epsilon. If this is less than epsilon, then this sure the hell is less than epsilon, and we're good to go. So now remember, now we're kind of back at the spot where we had something like this. We're kind of back to that point. So now I can say, all right, look, divide both sides by this, thus x minus x naught less than epsilon over 2 mod x naught. No, I shouldn't say mod, we're not doing, absolute value of x naught, it's not complex numbers. And think about this is a flow, thus this implies that f of x naught, or f of x minus f of x naught is less than epsilon. But that's only when x minus x naught is also less than 1. Also less than or equal to 1. So now we're going to incorporate. Now how do we take into account that we said this can't be more than 1, and if it's less than this, then we get what we want. So what we say now is set delta equal to the minimum of these two things. It's either going to be 1, if we don't want delta to be more than 1. So if this quantity here that I'm about to write up, which is epsilon over 2 x naught plus 1, if this thing is more than 1, then we're just going to default to 1, because we know all this stuff holds true when delta is less than or equal to 1. But if this is smaller than 1, then this will hold true. It still means that delta is less than 1, because we're taking the minimum of those two. And then this all just unfurls in this direction. Let me stop for a second. Then, if now we unfurl, we have both x minus x naught is less than 1, and it's also less than this beast here. it's less than both those things, because it's less than the minimum of these. Once we have this implies that x plus x naught is less than 2, let's see here, wait, 2 x naught plus 1. So f of x minus f of x naught is equal to x squared minus x naught squared equals, do our little factoring game. Less than 2 x naught plus 1 from this piece here times x minus x naught. And look at what we've said about x minus x naught. It's less than, so let's put a little star here, by star, that expression there is less than 2 x naught plus 1 times x minus x naught. But x minus x naught is less than this. So less than 2 x naught plus 1. I know, God, you must be like dying out there just hearing me say this shit over and over again. So I apologize. I guess I could write in silence, which maybe sounds worse. So if I've got this equals epsilon. And now I'm done. Yeah, I can see by Camila's face.
I got lost when we started the proof.
What's that?
I got lost when we started the proof.
You got lost when we started. Where'd you get lost at?
No, I like was writing after you, and then all of a sudden I like looked up and I was like, oh.
Where are we? Okay. Do you want me to kind of
No.
go through it again real quick?
I think I figured it out.
Okay.
Because I stopped writing, and then I started reading it. And
Okay.
I was like, oh, okay.
Okay, cool. And you're like, also, I don't want to hear you say all that. Fair enough. There's multiple reasons. So that's how that proof goes. Let's see what time. I want to make sure to give us time to do a little quiz. I've got a special guest coming to talk to my seminar afterwards, so probably it's kind of cut out here a few minutes early. I've got to figure out all the tech. And take a minute of that, looking at that, and let me know if there's anything you want to talk about. See Christian looking at it intently.
Is it always a good idea to just assume that delta will be less than or equal to 1?
It never hurts. You don't need it in those simple cases with the linearity. You could though. It would never hurt. So I wouldn't add it in where it wasn't needed.
Yeah, oh yeah, I just
Yeah,
think
yeah.
like for these kinds,
Yes.
will there ever be a case where assuming it's less than or equal to 1 will like screw us over?
Oh, gotcha. No.
Okay.
No. And so what if someone, just like really quick, let me kind of show you how this might propagate to other ideas and other proofs. Like if I asked you to show that f of x is x cubed, or that this function, f of x equals x cubed, is continuous at any point in the reals. You do the scratch work. Let's just look at the scratch work again. So I've got x cubed minus x naught cubed. This is my f of x minus f of x naught. Let's take that. I still want to somehow get out of that this, because this is the thing I'm going to set less than delta. So I have to find that quantity in here. Any suggestions on how we could rewrite this? If I put this, do you know what's left?
Is it x squared plus x naught squared?
It's pretty damn close to that. It's going to be x squared. It's all second degree terms that one could come up with. So x, and then you're right, Cormac, I got an x naught squared, but then I also have an x naught in there. So a really good thing, just math folk, if you have something squared or something to the nth minus something else to the nth, you can always break it down to get that minus the simple quantities out. And what's left over here is going to be all the n minus 1 power combinations. So I would definitely have that to the n minus 1. And they're all pluses too. And then I would have that to the n minus 2. To kick it back up and add a power, I get one of those. And then I just diminish these powers. So then that's n minus 3. Kick that up to that squared. And then eventually, you've got these guys on the flea, and you've got this guy here pumping up, and your last term is going to be that thing in the triangle to the n minus 1. So this is, I guess, kind of called a binomial expansion kind of dealing, but this is a great thing to have ready. Because then now, your goal in this proof, and I feel like you actually have this one as a homework problem. Do you have a cube? Did I know? Yeah, don't know yet. Not sure yet. We'll all find out this weekend. Cormac, you sounded like you kind of had looked at some stuff.
Yeah, I saw some questions about proving they're continuous, but I didn't see X cube.
That's good. That's good. That's exactly, you're looking at the right homework assignment. So what you're going to do here is you're going to say, okay, well, what if this is less than 1? Then what does that mean about this? And you're going to try to get that thing bounded. And you want something here that's pure X naught stuff. So that would be the goal, and think about how I did that. I got this, so that it's going to be something like, actually, sorry, it's, yeah, because there here we had the X plus X naught, and we got that bounded by this. So how could you do that if you know this is true? So taking this, I would write it as a double inequality. And gosh, where do we go from there? Oh, check this out. So this would mean that X, oh yeah, this isn't hard. That X is between those two numbers. And now you can get a bound on X squared. So X squared lives between the squares here. X naught plus 1 quantity squared, and 1 plus X naught. Well, that should be minus 1, shouldn't it? And that's squared. So now I've got a bound on this term that doesn't involve X. And then this X here, X naught, is less than just X naught times all that stuff. X naught has this property that X naught squared minus X naught is less than X naught X. I'm just multiplying through here by X naught. And you can get a bound that way. Slap a lot of absolute values on, get everything to be the most. But then that's the game. And now you could do this for literally any power of X. I won't ask you to, but you could. All right, I got one last thing I want to show you before we do quiz time. So for today's quiz, you only have that one definition of continuity. That's all you could have memorized, so that's the one that I'm looking for today. But I want to show one last definition of continuity. Suppose I've got this function f, and its domain is all the, it's just easier if we do it like this. So this function is defined for every real number. Could be like a polynomial, x squared, could be sine, cosine, cosine, any of those nice functions that are defined everywhere, e to the x. So suppose this, then f is continuous on R if for every open set U in the reals, F inverse of U is open as well. That's so elegant. Let's talk about what that means. So I've got a nice old continuous function right here. It's f of x and x. And this is saying that for every open set, I pick in the range. So U lives here, because I'm going to take f inverse of it. For every open set, if I pull back to see its inverse image, so this down here would be f inverse of U. Down here, this little set. That no matter what I pick for U, its inverse image, as long as this is open, then this is open. And that's a super wild, like elegant definition of it. I'm not going to have the time to prove it today, but we will talk about it on Monday. But this is the nice topological definition of continuity. Let me show you how it would be super useful. Let's take a nice function that looks like this. So just a step function, jumps up 1 unit. Like that. Now we can see that's not continuous, right? It's got a big old break in it. It doesn't have the limit property. The limit does not exist here at, oh hell, let's just call it 1 right there. So we know that this is not continuous for a variety of reasons. But let's take an open set around 1. So I'm going to take some open set that looks like that. That's going to be my U. Just a tiny little open set. Maybe U is some ball around, let's see, that point was 1. Ball around 1 of radius, just a quarter. So it doesn't go down too far. What is the inverse image? In other words, what are all the x values that land me in there? So for this one, f inverse of that U is equal to what x values go in there. The first one is 1, and then everything up to infinity. Notice how, if I let x be 1, so because, let me write this a different way, you might not be used. F of 1 infinity is just an element of U. Everything from 1 on up lands me in that strip, but this is closed right here. It's not open. So it's a really wild way to detect continuity, but we'll get more into it on Monday. It's like a cool thing that I've been looking forward to telling you all semester. Pretty neat. Let's do a quiz, friends. This shouldn't take too long. I'll put the stuff up on the board. Alright, so I just need a few things from you today. And these are the definitions I need, please. Definitions. Number 1 is open set. Here, let me get you rolling here. We would say that O is an open set if, please complete that definition. Number 2, F is a closed set. Give me any of the definitions of closedness. There's several. Closed set if, fill in the blank. Number 3, K is a compact set. Give me any of the definitions for that. I think I asked for all 3. Give me 2 of those. give me one way of telling and a second way of telling, and then number 4 is F is continuous at X naught in its domain if fill in the blank. Thank you.